In this section, we'll take a look at the High Availability Concepts objective of the JNCIS Service Provider exam. We'll examine the theory of VRRP, link aggregation, GRES and NSR, and we'll also take a look at ERP or ERPS. For more detailed coverage of this objective and more, please check out the JUNOS Intermediate Routing and Juniper Service Provider Switching courses.
In this video, we're going to talk about VRRP, or Virtual Router Redundancy Protocol. And this is used as a first hop redundancy protocol. So it's providing resiliency to devices that don't have any routing capability. So PCs, servers, that sort of thing. And it's providing resiliency for the default gateway IP address that's configured on those servers, on those PCs. So let's take a quick look at the basics of VRRP operation. In VRRP, you have a master router and one or more backup routers. The master router is sending VRRP packets out to a multicast address, and all the backup routers are listening to that multicast address. The backup routers aren't sending any packets. They don't send any packets as long as they continue to receive these VRRP packets, and the priority listed in those VRRP packets is better than the priority that they have configured. If they stop receiving VRRP packets, i.e. the master has failed, or they now see their priority as better, i.e. a reconfiguration has taken place, then they assume the mastership role and they start sending VRRP packets. And so this is the election of the master within VRRP. The resiliency comes in that you have a virtual router, a virtual IP address that the master is responsible for. And what the master is going to do is the master is going to respond to ARP requests for that virtual IP address. So this virtual IP address is configured as the default gateway on the hosts that we're providing resiliency to. So when they come online, they send ARP requests for that virtual router IP address, and the master responds. So they route traffic out to the network via the VRRP master. Should that master fail and another VRRP router assume mastership, he then responds to ARP requests for that virtual router IP. So these hosts then switch sending traffic to their default gateway via the new master. So this is how VRRP provides resiliency for the default gateway of non-routing devices. This is a quick overview of VRRP. In this video, we're going to take a look at link aggregation. So we can aggregate multiple physical links into one logical link using a standards-based protocol called LACP, or Link Aggregation Control Protocol. And this is what we have here on the board. And Link Aggregation Control Protocol can be used to build link aggregation groups, or LAGs, between a multitude of different devices for many purposes. We can use it, as is illustrated on the board here, to provide extra resiliency between a switch and a consuming device, a server, a PC, for example. We can be using this to increase capacity as well. So rather than this just being a resiliency purpose, we can have 2 gigs of capacity with 2 gig E-links rather than just 1 gig E-link. And this approach can be used between switches, between routers and switches for the same purpose. This is particularly useful when you're interconnecting switches, because it means that you can increase resiliency without the need to run a cumbersome protocol like spanning tree, for example. So this is link aggregation between 2 devices. Now, obviously, we're increasing resiliency here, but there is still a single point of failure. If this switch were to fail, we would still completely isolate this server. So there is an alternative to this, and that's multi-chassis link aggregation, where you can have a server, a PC, any client device basically, and have that interconnected to two parent devices. And this is what we've got illustrated on the bottom side of the board here. So it's key to note here that multi-chassis lag is a Juniper proprietary feature, whereas standard lag using LACP is a standards-based protocol. So with multi-chassis lag, as far as the client device, in this case our server, is concerned, he's running LACP to the same device. On the service providing side, we have multiple different switches, and they are propagating state between each other using a protocol called ICCP, or Inter-Chassis Control Protocol. Again, this is a Juniper proprietary protocol. And because we're propagating state between our two switches, we can provide a link aggregation group to our client device, our server, as if that aggregation group was configured and deployed only on one device. And this is a quick overview into link aggregation. In this video, we're going to talk about routing engine resiliency. So we need to be able to sustain failures when a routing engine fails on one of the chassis that we're managing. Otherwise, if the routing engine fails, the whole device is lost and all traffic running through it is dropped. So the first way that we can do this is, if our chassis can support it, we can install multiple routing engines, as we have here on the board. We have a master routing engine, RE0, and we have a backup routing engine, RE1. And what happens in this scenario is that the master routing engine is propagating all of the routing and switching state into our line cards that are actually doing the packet forwarding on the device. And should the master routing engine fail, the backup routing engine assumes mastership and then starts programming the line cards. Now, what happens when this occurs is that the line cards reboot, and they do this to clear their state before reforming adjacencies with the new master routing engine. Then they have all the new state programmed to them. And the routing engine state has all been cleared as well. So any BGP sessions, OSPF sessions, etc. have all dropped and then all re-establish on the new master. And this process takes time. We're looking at multiple minutes for this to occur. All the while, you're dropping traffic on your chassis. So obviously, this is far from ideal. So there are a number of different ways that we can improve the convergence in a multi-routing engine chassis. The first is to use the GRES protocol. This is Graceful Routing Engine Switchover, and it's a Juniper proprietary protocol. So what we're doing here is that in a multi-routing engine chassis, the master routing engine is propagating the interface and kernel state to the backup routing engine. So that's all the state regarding interfaces on the line cards. So what this means is that if we now have a master routing engine failure, the line cards no longer need to reboot when they reform adjacencies to the new master. So this significantly improves convergence times. However, in this scenario, we are still resetting all our control plane state on the new master, because the new master has no awareness of BGP routes, OSPF routes, etc. So what happens here is that the master fails, the backup immediately takes over and reforms adjacencies to the line cards. The new master then has to reform control plane adjacencies to all his router neighbors. And we're improving convergence here, but we're still looking at tens of seconds of downtime. This downtime is going to vary depending on the amount of control plane state that we need to relearn on the new master. So there are still further improvements here that we can add. And this is by adding non-stop routing or non-stop bridging This is dependent on whether this device is a router or a switch or a mix. And what we're doing with non-stop routing, non-stop bridging, is that we are adding this on top of GRES functionality. We still retain GRES, propagating kernel and interface state from master to backup. And we now have NSR, NSB, propagating control plane state. So your MAC address switching table, all of your routing tables, all of your BGP adjacency information, OSPF adjacency information, etc. All of this information is propagated from master routing engine to backup routing engine. So now, if the master routing engine fails, we no longer have to reset control plane adjacencies. We no longer have to repopulate our forwarding tables on our new master. So this is now reducing the downtime on the device to potentially the sub-second level, again dependent on the loading of our control plane and the precise protocol mix that we have in our control plane. So obviously this is a much more beneficial scenario than just having the two routing engines alone. And this is using NSR or NSB in conjunction with GRES. These protocols also have another benefit, and that's that they can dramatically reduce the amount of downtime exposed when we upgrade the software on a device. This is when we use a feature, and this is another Juniper proprietary feature called in-service software upgrades. And it uses this GRES and NSR architecture in the background to allow us to upgrade one routing engine at a time and then do stateful failover in the background so that we're minimizing the amount of downtime as software images are upgraded on our routing engines. And one final thing to note in this routing engine resiliency video is that there is a standards protocol that provides routing engine resiliency, and this is graceful restart. So you don't find it used much anymore, but in certain scenarios it can provide some benefit. Those scenarios are where it is only ever possible to have one routing engine. So you have control plane and data plane separation, so you have a routing engine and you have line cards that are supporting the data plane, but you don't have multiple routing engines. And what graceful restart allows us to do is, through the use of helper devices, so other routers bordering the device that we configure graceful restart on, it allows the routing engine to restart, and rather than having the data plane restart with it, the data plane stays up and continues to forward packets, and we wait for the routing engine to restart. Once the routing engine has restarted, he reforms adjacencies to his neighbor devices, and then he re-updates the data plane. And this is a quick overview of routing engine resiliency. In this video, we're going to take a look at ERPS, or Ethernet Ring Protection Switching. Now, if you have an Ethernet network that only consists of a ring, ERPS is a good alternative to spanning tree. It has some significant convergence improvements over spanning tree. In fact, under optimal conditions, ERPS can converge within 50 milliseconds. But it has to be emphasized that we have to deploy ring structures for ERPS to work effectively. So let's now quickly talk through the basics of ERPS. Within ERPS, we nominate a ring protection link, a RPL. And this ring protection link is blocked under normal operation. And the blocking of this link means that we're removing the loop from our ring topology. We achieve the block on the RPL by nominating an RPL owner. We're nominating one of the switches that's interconnected to the RPL, the ring protection link, as the RPL owner. And it's the RPL owner's responsibility to place a block on the RPL when the ring is operating under normal conditions. It's also the RPL owner's responsibility to flood ring automatic protection switching packets out, our APS packets out, to the rest of the network to inform devices connected to the ring that the ring is operating under normal conditions. So what happens in the case of a link failure? Say the link between switch 1 and switch 4 fails. So a number of things happen. Switch 1 and switch 4 place a block on the failed link, and they then start to flood our APS messages. These switches flooding our APS messages causes the RPL owner to stop flooding our APS, and it also causes the RPL owner to unblock the RPL. And the unblocking of the RPL restores connectivity to the ring. So that was reactivity to failure. How does ERPS react to link recovery? So again, let's turn to switch 1 and switch 4. Say the link between switch 1 and switch 4 now recovers. So for the meantime, switch 1 and switch 4 retain the block on the link, but they change a flag in the RAPS packets that they're flooding. And this change of flag in the RAPS packets that reach the RPL owner cause the RPL owner to trigger a timer. Once that timer has expired, the RPL owner places a block on the RPL again, and he starts to flood RAPS packets again. When they reach the devices connected to the now recovered link, that is the trigger for these devices to remove their blocks on the recovered link, and the ring returns to normal operation. And that was a quick overview of ERPS.